Thank you for joining the Waters and Stanton video channel. Coming soon is the new Zego noise reduction and filter unit, a unit that promises to digitally process and reduce background noise as well as providing additional filtering. This unit will work with any HF or VHF transceiver. It also includes a 3-watt audio amplifier, so it will drive an external speaker or of course headphones. Further details on our website. That looks an interesting unit, so I look forward to testing it out. I think we'll have them in about 3 weeks' time, as from we're in the middle of April now, so we should have them early May 2022. And anything that promises to reduce noise is always very welcome, so I'll get my hands on one as soon as I can and let you know how it gets on. But the topic of this video is verticals and how you can improve the, I've said DX performance. I hesitate to use the word DX because DX is a bit of a vague term. I mean, what is DX and what isn't DX? I think DX is what you perceive it to be. But anyway, what I'm going to do is to talk about vertical antennas, my experiences, what I've found, and to some extent what theory supports. You know, there's not too much difference between various vertical antennas. If we talk about a quarter wave vertical, I mean that's the most popular vertical that ham radio users employ. A vertical antenna, a quarter wave vertical antenna, and they plop it on the ground and they feed it with some coax cable and they hope that they'll get some good results, and many of the users do get good results. I've used vertical antennas for many years, but I did publish a video about probably 2 months ago now where I really underlined the fact that perhaps we weren't getting the performance from a vertical antenna that we were expecting. You know, if you model a vertical antenna, there's no doubt that you get some good low-angle radiation. In fact, it's predominantly low-angle radiation. Low-angle radiation means the signal travels further, and I suppose we can say that's DX performance. It's great, isn't it? You model it, there you are, problem solved in a back garden. You've got a fairly reasonable and easily installed aerial, and it's going to give you DX performance. Or is it? The problem with antenna modelling, particularly for vertical antennas, which I'll explain in a minute, is that it tries to live in the real world, but it doesn't actually live in the real world. I mean, if you look at something like the MMANA program, you can actually select the ground beneath the antenna, and the idea is that will give you some idea of the performance you're going to get in your particular location. But again, it doesn't actually tell you the whole story. It tells you what the antenna should do, but it doesn't tell you what it actually does. Now, one of the reasons is that we have something called a Fresnel Zone, which is a zone which extends to several half waves away from the base of the antenna. And that ground, that expanse of ground, well beyond your garden, has a very profound effect on the performance of the antenna. Now, if you're in the average garden or a small garden, you probably have got trees. You've got the next door neighbour's house full of house wiring. You've got power cables, you've got telegraph poles, all sorts of objects that will absorb the signal. Now, the modelling program doesn't know anything about that. The only way you could really replicate that is to use one of the really advanced three-dimensional programs, which is beyond the expense of most hams, and probably would spend ages trying to model it. The Fresnel Zone is also interesting because it's really calculated in lengths of half waves. In other words, so many half waves is the critical zone at which the performance of the antenna is affected by that area. As you go higher in frequency, so the distance reduces. So if you're operating on 10 or 12 or 15 metres even, the Fresnel Zone is a lot shorter than it would be on some of the lower frequency bands. And that's probably why a lot of people, including me, find that you get quite a pronounced improvement in performance as you go higher in frequency. It's not that the antenna performance changes so much as the ground around it has less effect, because the Fresnel Zone doesn't have to extend, or doesn't extend so far as it would on lower frequencies. So the first way to improve the performance of your vertical antenna is to operate on the higher frequencies, providing the bands are open. As I said at the outset, there's not much difference between vertical antennas if we're talking about quarter waves. And when we come to multi-band antennas, well, there's not too much difference there either. If you have a trapped multi-band vertical, it tends to be pretty efficient. I've really never really noticed any difference in performance between for example, a full-size 20-metre vertical, which is 5 metres tall, and a trapped vertical, which is probably around about 4 metres tall. The only noticeable difference is that the bandwidth of the trapped antenna is slightly narrower, but it is self-supporting. It gives you several bands. You can have parallel tuned vertical elements. In other words, you have a vertical element for each band, and that performs about the same. There's probably a slight reduction compared with a full-size antenna, because you wouldn't normally put a quarter wave next to a non-resonant length of wire. But in this antenna you do, and from what I understand, there's very little difference in performance. It tends not to be self-supporting because a multi-element vertical is not so easy to support without radials, without guy wires, but it works just as well. So for all practical purposes, a monoband vertical or a trapped vertical or a vertical that has several elements works very similar. Therefore the performance is going to be very similar, and the drawbacks are going to be very similar. Now, I think many of us realise that a vertical antenna has to have radials. It's one of the essential items of a vertical. You could put a copper pipe in the ground and it will work, and you'll probably get quite a good VSWR, because the actual feed impedance of a vertical, ground-mounted vertical, is around about 30 ohms, give or take an ohm. So it's about 30 ohms. So it's well below the 50 ohm coax cable impedance. Therefore, you're going to get a mismatch. Therefore, you're going to get a bit of VSWR. But if you drive a copper pipe into the ground, and that's your only earth, you'll probably get quite a good match. And the reason is because you've got an earth loss, and that earth loss appears in series with the antenna feed. Therefore, your 30 ohm low impedance becomes something like 50 or 60 ohms. Get a good match. It's a good example where a lower VSWR actually means the antenna's not working as well as it could do, because as you add radials, as you lay wire radials on the ground, then you improve the performance, you reduce the earth loss, but you also reduce the feed impedance, or the apparent feed impedance of the antenna. But radials are an essential part of the antenna. It improves the performance, it makes it more efficient. How many radials do you put down? Well, that's an interesting question. How long should the radials be? Another interesting question. I think we've been taught that radials should be a quarter wave long and we should get as many as possible on the ground. Well, I suppose that's not a bad rule of thumb, but I think many users will tell you that You don't need radials a quarter wave length long. You can use radials half that length. In other words, you can use radials that are about an eighth of a length long. And I think those that have done a lot of work on vertical antennas will notice that it's really the amount of metal that you put on the ground rather than the dimensions of it that is important. The trouble with wire radials is that the law of diminishing returns quickly comes into place. Once you've got more than about 16 or 20 radials on the ground, you've got to put an awful lot more on the ground to notice any difference. And what improvement do you get with a good earth system or a good radial system compared with just a few? Probably about 2 dB. You get about 2 dB of improvement if you spend a lot of time laying down the radials. 2 dB is very worthwhile having, of course. It's 2 dB of gain. You never turn your nose up at gain. So if you want to improve the DX performance of your vertical antenna, you lay down as many radials as you can. But you very quickly hit the buffers. You can't go any further. You're stuck with 2 dB of gain. Now, there is an interesting option that I've explored and many others have explored, and there's some interesting papers on the internet all about this, and this is using elevated radials. Elevated radials is what the name suggests. Instead of laying the radials on the ground, which of course on the ground they're non-resonant anyway, if you raise the radials to a height of say a metre, and generally speaking, the lower in frequency you go, the higher above the ground the radials will be. But for 20, let's take the 20 metre band. If you were to install radials or elevated radials at a metre above ground, something happens. You get an improvement. Now, this improvement has been documented on the internet, but I've been experimenting over the last year with elevated radials, and I have to say that you do notice a significant difference. It's difficult to evaluate it because you can't switch it on and off, but over long-term tests that I've been carrying out, certainly elevated radials make an improvement. You might say, well, wait a minute, hold on a minute, elevated radials are all okay, but it's going to be a bit of an eyesore. Well, it doesn't have to be. There's an interesting paper on the internet published by Step IR, and that suggests that 2 raised radials will give you a great improvement and be better than many radials laid on the ground. Now, I'm not quite sure how accurate that claim is, but certainly I've added 2 radials to my ground-mounted antenna, and I've certainly noticed an improvement. These raised radials don't require you to change the height of the antenna. You can still mount the antenna on the ground, but what you do is you connect a couple of quarter wave radials. Remember that because they're raised, they've got to be resonant. You add a couple of quarter wave radials to the band in question. In my case, it was 20 metres. And you take them from the base of the antenna and immediately take them at an angle of about 45 degrees up to a post, which is a metre high, a bit of wood in the ground, metre high, and then another bit of wood, a quarter wave away, which is also a metre high, and you then have a pair of raised radials. One goes in one direction, one goes in the other. In other words, 180 degrees. 2 radials coming away from the base of the antenna at 45 degrees to a post about a metre high, and then another post at the required distance, so you've stretched out 2 quarter wave radials. Here you can see the radial coming up from the base of the aerial at an angle of 45 degrees, and it goes up to that cane I've stuck in the ground, which is about a metre high. Now, there's a very easy way of resonating the radial. Just get yourself an antenna analyzer, a bit of copper wire, tin copper, tap that onto the earth side of the aerial system, connect the radial to the live side of the antenna analyzer, and you'll resonate it very easily with a very pronounced dip. I have to admit that I was a bit dubious when I first read this, but there were several papers on the internet that gave reasons why it should work and how it works and all sorts of mathematical equations and so forth. I tend to be a guy that wants to try it out for myself and just see whether it does work. And I have to confess, it does work. It's worked extremely well. I've noticed significant improvement. But this leads me on to something which I think is even more interesting. When I was first on the air back in 1960, one of the first commercial antennas I bought was a high gain 12 AVQ, which covers 10, 15 and 20. I think it's still available actually. A trap vertical, self-supporting. And I put it on the side of the house, and I had 2 radials for each band, 2 resonant radials for each band. And the interesting thing is that in those early days, I say early days, go back to when I was first licensed, most hams would never think of putting a vertical at ground level. The convention was to have the vertical in the air with radials coming down at around about 45 degrees. The great thing about that was that the radials coming down at 45 degrees give you an improved or higher radiation resistance of the antenna. So the antenna matches 50 ohms much better than it would do with radials coming out horizontally. The antenna is in the air. It's not obstructed nearly as much as it would be on the ground level, and that was the convention. It was very unusual to have ground-mounted vertical antennas in those days, unless you were on the LF bands, perhaps certainly 80 metres and 160 metres, and maybe 40 metres. But for the HF bands, you would always put it in the air with 45-degree angle radials. And it worked. It worked very well. There was one station that was in Essex, actually not too far from where Louis Varney used to live, G3OJV, and he was regularly on 20 metres working the Pacific on a raised vertical. I don't know how high it was, but it was a raised vertical on a mast, and he had several resonant radials on each band, and it worked extremely well. And if you think about it, you're almost using a vertical dipole. And the vertical dipole works extremely well as well. So, are we using vertical antennas in the right way? Should they be at ground level? No, I don't think they should actually. I think if you've got the ability to raise the vertical antenna in the air, certainly for 10, 15 and 20, raise it in the air, use 45-degree or thereabouts radials. And I reckon you'll get a significant improvement in performance. I'm going to do some work this summer on that and just see how I find it works, because I've operated for so long. I know exactly what I would expect. I can sort of think, okay, this is the sort of experience I get with a vertical at ground level. Is it going to improve when I raise the radials a metre above the ground? Yes, it has done. I've tested it over a period of time, and I'm convinced now that it's given me a couple of dB or so improvement in DX gain. And I'm willing to bet that if I reposition the antenna, say 16 or 20 foot above ground level with 45-degree radials, I reckon I might get another 2 dB worth having. So there we are. This video is really about my own experience. It's not based on theory, it's based on practical experience. But that practical experience is steered by theory. I've got antenna bolts going back to the 1950s, and we know what the radiation pattern of a vertical is. It's been documented many times. You don't need to model it. Although modelling, I wouldn't say anything against modelling because it's very educational, but just be aware of the results. So, thank you for watching this video. I hope it's giving you some food for thought. Perhaps in the summer you can get out in the garden and play about and see what you think. You let me know what you find. You may disagree, you may be pleasantly surprised. That's the joy of ham radio, isn't it? Experimenting and sometimes being very surprised in a pleasant sort of way. So thank you for watching this video. Take care, enjoy ham radio. Look forward to seeing you in the next video.